As you know, there are a lot of efforts to use the ocean to hide CO2. It's called the ocean carbon dioxide removal or ocean CDR. And what is the most natural ocean CDR? Of course, it's the biological pump. Ocean has a solubility pump where, CO2 is highly soluble in water, so it dissolves into the ocean, and there are places where it sinks away. There are places where the ocean brings it up. Ocean itself has a lot of CO2 because of this dissolution, plus its ability to move CO2 dissolved into the water as through CO3 into bicarbonate and carbonate ion. We call it the buffering ability, so the ocean doesn't get saturated with the CO2 because of that. This paper is kind of long. It's about the biological carbon pump estimated based on multi-decadal hydrographic data to see how much CO2 is getting down into the ocean and what will happen with this ability due to global warming and so on. So the abstract is that the transfer of photosynthetically produced organic carbon from surface to mesopelagic waters draws down carbon dioxide from the atmosphere. However, current observation-based estimates disagree on the strength of this biological carbon pump. The Earth system models also exhibit a large spread of BCP estimates, biological carbon pump estimates, indicating limited representations of the known carbon export pathways. Here we use several decades of hydrographic observations to produce a top-down estimate of the strength of the BCP with an inverse biogeochemical model that implicitly accounts for all known export pathways. Inverse modeling is where you use the data itself to estimate something with observations as the constraint. You have to know how that works, of course. Our estimate of total organic carbon export at 73.4 meters, modeling photic zone depth, where the light is enough for photosynthesis, is 15 petagram carbon per year with an uncertainty of plus minus 1.12 petagrams per year, with only two-thirds reaching 100-meter depth owing to rapid remineralization of organic matter in the upper water column. So TOC, total organic carbon, is falling, but it gets recycled and gets converted back into inorganic carbon within the top 100 meters to the extent of two-thirds of the total that's falling below 73.4 meters. Partitioned by sequestration time below the euphoric zone, tau, the globally integrated organic carbon production rate with tau greater than 3 months is 11.09 petagram carbon per year, dropping to 8.25 petagram carbon per year for tau greater than 1 year, with 81% contributed by the non-advective diffusive vertical flux to sinking particles and vertically migrating zooplankton. Nevertheless, the export of organic carbon by mixing and other fluid transport of dissolved matter and suspended particles remains regionally important for meeting the respiratory carbon demand, that is the feeding of other heterotrophic organisms. Furthermore, the temperature dependence of the sequestration efficiency inferred from our inversion suggests that future global warming may intensify the recycling of organic matter in the upper ocean, potentially weakening the biological carbon pump as far as sequestration out of the water column is concerned. The paper has kind of a summary that I'm going to read off. Oceans can capture more carbon dioxide than previously thought. The strength of the biological carbon pump was estimated using direct measurements of nutrients collected over decades. The findings indicate that ocean waters can capture and store larger amounts of carbon dioxide than previously estimated. This might have implications for climate change models. The problem: marine algae in sunlit zone within 200 meters of the surface produce organic matter from carbon dioxide, process known as primary production. The resulting matter is then transferred to deeper waters through several pathways. The combination of these processes is called the biological carbon pump, which removes CO2 from the atmosphere, captures it in the organic matter, and stores it in the ocean where it can remain sequestered anywhere from days to thousands of years. You may have heard of the biological pump and solubility pump before. If not, I have a full course on carbon cycle that you can follow up with. The pump is therefore an important regulator of Earth's climate because it is impossible to directly measure this carbon transfer at global scales. The strength of the biological carbon pump remains uncertain, with model estimates ranging from 5 to 12 petagram carbon per year. The solution to this problem, the biological carbon pump can be inferred from concentrations of several tracers, such as nutrients, oxygen, and carbon, for which direct measurements collected by ship expeditions are available. Uh, Spanning multiple decades. Respiration, the breakdown of organic matter in deep waters, leaves subsurface waters enriched with dissolved inorganic carbon and depleted in dissolved oxygen, because respiration takes energy and respires it into CO2, takes oxygen as well. From these observations, the rate of carbon export or transfer to deep waters can be quantified by inverse models, which estimate a variable from the observable changes that it induces in, let's say, nutrients and oxygen and carbon, right? So we developed an inverse model that provides an excellent fit to the available observations. It can be used to estimate the strength of the biological pump in terms of how efficient it is at pumping down the organic carbon without having to measure the individual carbon fluxes. The estimated flux of the biological carbon pump is 15 petagrams of carbon a year at a depth of 73 meters. This quantity of carbon is consistent with the estimate oxygen consumption at depth and is therefore sufficient to meet the carbon demand of mesopelagic organisms which are waiting for this carbon to come down. This result contrasts with some estimates obtained using in situ measurements. Those models sometimes have had difficulties balancing the metabolic energy needs of the mesopelagic community with the supply of energy-rich organic matter, possibly because some organic matter export pathways might be missing because it's difficult to do observations year-round. So you know what energy is needed for the living organisms below the sunlit region, how much has to come down, but you are not able to match that number. Our models estimate the strength of the biological carbon pump. Our models estimate of the strength of the biological carbon pump captures the annually averaged export of all organic carbon transfer pathways. Thus, it provides a helpful baseline with which to calibrate models used to predict climate change. As such, it is much more robust than satellite observation based estimates that rely on noisy measurements and potentially biased algorithms for calculating the net primary production and carbon export. So people do it directly from satellites, but this paper argues that's problematic. Our model finds that transfer efficiency of organic carbon from the sunlit zone to the subsurface ocean is lower in regions with higher sea surface temperatures than in cold regions. We therefore speculate that efficiency of the biological carbon pump will decline in response to global warming. However, our model cannot establish whether the correlation is causative, nor can it provide a definitive explanation for the inferred correlation. More research into this temperature dependence of the individual processes responsible for the carbon export is needed. Another important limitation of the study is that our model is built on the assumption that the processes do not change over time. Decades of estimates based on inverse model that is stationary. If the pump is changing in response to global warming and other perturbations, our model would average these changes without detecting them. To detect changes in the ocean's biological carbon pump, further measurements obtained by ship expeditions such as those that made our research possible and a careful analysis of the differences between the measurements and predictions will be essential. Future developments of our inverse model should include the effects of seasonality to estimate the amplitude and phase of the pump's seasonal cycle. We are working on improving our model with this goal in mind. We are also including more nutrients and carbon isotopes to further improve the robustness. Okay, so I think I might have missed a figure there, but let me do that. Da, da, da. Let's see. I can quickly do it then. No, actually I didn't. Yes, I did miss the figure. So uh, let me just bring up the figure on expert opinion so that we can quickly add that here. I have to run soon, but nonetheless, I will try to do this. Oops, I screwed it up. doing this while recording is not a smart idea. That's not the way to do things, but sometimes I'm not very careful in preparing these. I try to do this when I have free time, and sometimes uh, I hurry, right? So a groundbreaking merit of this work, this is the expert opinion. This groundbreaking work merit of A groundbreaking merit of this work is solving a long-standing caveat that has persisted in previous models and explicitly integrating distinct carbon export pathways. The authors report an increased strength of the biological carbon pump, which has far-reaching effect on the reconciliation of classical conundrum regarding the carbon imbalance between upper layer supply and demand at depth. This is extremely timely work for the community. So happy news, good news. So the figure here, figure one, distribution of the flow of organic carbon, which is showing the regions, cold regions are producing more. So this is distribution in milligrams carbon per meter cube per day. So volume and meter square per day, that's the flux, sorry. So upwelling regions and cold regions versus warm subtropical regions. And here you are looking at labile dissolved organic carbon, refractory, total organic carbon, semi-labile, and vertical fluxes with the time in years. Okay, what do you do with this? Basically, these are estimates. Labile is something that is reactive, refractory is not, and total organic carbon, semi-labile, and the vertical flux of particulate organic carbon. So it gives you a sense that most of it is not is going to disappear very quickly in terms of the number of years, and what lasts longer is refractory and uh, no, this is the yeah refractory DOC, and the blue one here is semi-labile DOC. Okay, so it gives you the pathways by which the uh, export out of the sunlit zone is happening and getting sequestered for a few years or longer, depending on which uh, form of organic carbon it is. Okay, so see you in the next topic.